Welcome back. I hope you had a good break. Now, we've been talking about the directly proportional relationship. I want us to look at this in a little bit more detail and look at another example, one that we've seen before. In fact, it's a very famous experiment that was done by a man called James Hook. Let's go and have a look at it. So, James Hook developed this idea of looking at a spring and putting a force onto a spring, which he measured in newtons, and he developed a relationship called Hooke's law, where he related the force that he was applying to the stretch of the spring, the increase of the stretch, in effect, or the extension. We refer to that as delta x, the extension of the spring. Now, which one do you think James Hook was controlling? Which one did he have the influence over? Was it the force or was it the extension? Because you see, we need to decide which is the independent variable and which is the dependent variable. Can you make a decision? Have a look at it carefully. The force was applied and it caused the spring to stretch. So that tells me that the force is actually the independent variable. And the stretch is going to be the dependent variable. Now, if we've got an independent and a dependent variable, and we're going to draw a graph of that, where do they go? Well, you need to remember this. The independent variable always goes onto the horizontal axis. The dependent variable always goes onto the vertical axis. So when we draw the graph, we're going to draw it like this, where we say the force, that's the independent, and this one is the dependent. And we're going to construct the graph. And what you notice in this situation is that we've got the words written as the title of the graph, where we take the first thing is the dependent variable, and we say that that's the relationship we're looking at, the dependent versus the independent. And it kind of goes in that order, which sometimes confuses people. So it's very important that we see this relationship from the graph of what's dependent, what's independent. And the next thing is to look and see the characteristics of this graph. Notice that the graph goes through the origin. So it is halfway there to being a directly proportional relationship. It covers that one condition. It goes through the zero. The next thing we notice, it forms a straight line. That tells us the gradient is constant. So it is in the same format as a straight line graph. And so it has a constant gradient. We can work out the gradient by looking and seeing the change in the force. So the change in the force would be written over there, and the change in the extension would be written over there. And we can measure that by looking at the different coordinates on a piece of graph paper and working at that. In the end, we're going to take the value for the dependent variable and divide it by the value for the independent variable. And in the end, we're going to say that because of the graph structure, we've got the change in x is directly proportional to the change in f, or simply x is directly proportional to f. This little alpha sign says in shorthand directly proportional. But now I want us to try and go from this graph to what the equation would look like. Yes, we've got an equation for the constant, for the gradient, and in Hooke's law, this gradient is called the spring constant. It's just a value for every spring, how stretchy a spring is. If it's a very hard spring to stretch, the spring constant will be a high value. If it's easy to stretch, then it will be a low value. We give the spring constant a letter K. So if we're going to put dependent, independent, and the constant together, to make an equation, well, that shouldn't be too difficult. Let's see how we can do it. We're going to take it one step at a time. We're going to say, there we go. We know that the delta x, the extension, divided by the force is going to be the constant. That's going to be the spring constant. Now, I'm going to multiply both sides of the equation by that factor, the independent variable, the force. And I'm going to get delta x is equal to k times delta f. Now, that might not be very convenient for me to work with. So I'm going to switch them around. I'm just going to rewrite what was on the right-hand side here. I'm going to write exactly that on the left-hand side. And what was on the left-hand side, I'm going to write on the right-hand side. And now you can see that I've got the value k times f is equal to delta x. But guys, I really want to be able to solve for what force is going to cause a certain extension. So if I want to know force on its own, I'm going to have to take this value here, the k that I originally had, and divide it by both sides, and I'll get a 1 over k there. Now, if the equation is written like this, f is equal to 1 over k times delta x, then what I need you to understand, it's not the gradient. The 1 over k, if we go back to the graph of the gradient here, this was k. If I'm working with f is equal to 1 over k delta x, then I've got to recognize I've changed something. And I hope you can see what I've changed. I've switched over and I've made this now the dependent variable. And this is now the independent variable in the equation because I switched sides. So you've got to be very careful when you look at a graph and they say, what does the gradient represent? Be careful that you look at what the labels on the graph are and make sure that you don't mix up the k value. This is not, the k here is not actually the spring constant. 1 over k would be the spring constant if we're wanting to be totally strict about it. Okay, so please be very careful. Whenever you're looking at gradient, try and interpret what it is, but make sure it fits into the form of y equals mx, where this is the dependent and this is the independent. Right, here's another situation, a graph that we've seen before. In this case, the volume is the dependent variable. I'm just going to write DEP there. And on the horizontal axis, we've got the independent variable. And in this case, it's 1 over pressure, or the reciprocal of pressure. Now notice this graph line cuts through the 0, 0 point. We also recognize it's a straight line. And so the gradient is constant. And so we've got a recognition here that the change in volume and the change in 1 over pressure, if we took those two and we put them over each other into an equation like this, that this will form a constant. So what can we say based on the graph? Well, I think we can say, based on this graph, that volume is directly proportional to 1 over pressure. And that's a very interesting conclusion that we've come to, because it's telling us about a proportional relationship, but it includes a 1 over, a reciprocal. That's quite a word that we don't hear very often, but it's an important word to remember. Now, let's see the implication of what this gradient is actually representing and how we can use it to find further relationships. So as I've written it in words here, we've written it in symbols previously to say the volume is equal to 1 over pressure. we've written it in that form, we're saying this is a constant. What I want us to do is just to look at this very carefully and say, if we've delta V over delta 1 over P. Now, what's the rule when you divide by a fraction? That's right. If you divide by a fraction, we say we tip it and we times it. So we know that's equal to a constant. So delta V times 1 over P, or delta 1 over P, is equal to a constant. So in effect, what we can say is that V times P is equal to a constant. Guys, that's quite a discovery for us, because now we can say that when we've got two variables that are multiplied together, they are not forming a directly proportional relationship, but we recognize that it's the reciprocal that is directly proportional. It's 1 over the pressure that's directly proportional to volume. What we can say when we see this sort of relationship coming out is that those two things, when they multiply together, they're called inversely proportional. Now, in the likes of the pressure volume graph, what they sometimes represent this is say, let's just take some readings and let's say they're equal to each other. And if you look very carefully at that sort of relationship where you take points and you multiply them together and they give you a constant, well, that's going to not give you a straight line if you plot it, but it's going to give you a hyperbola. So we're going to say if we have pressure and volume, we're not going to get a straight line in this case, but we're going to get a hyperbola that looks something like that. But remember, a curve, we can't really tell. Is it a hyperbola or is it a parabola? Is it another function? Well, it's much easier to recognize whenever you have an inversely proportional relationship. If you plot 1 over the independent variable against the dependent variable, you'll be able to get a straight line. Okay, so let's make sure that we've got this very clear. When we represent graphs, we must make sure that we try and show a directly proportional relationship. Directly proportional relationship will always have a straight line that passes through the origin, where an inversely proportional relationship, it might come up that we've got a curved line. To try and satisfy that, what we're going to do is we're going to say the following. We're going to say, instead of choosing the dependent variable and the independent variable, we're going to change that around and we're going to say, let's take the y, 1 over x, and then it will be a straight line. It will pass through the origin, and we can say that y is directly proportional to 1 over x. So please make sure whenever you're trying to look at relationships and you're trying to look at graphs, relating them to an equation, that you must make sure that you've got them very clearly sorted out, that you understand what is the independent variable, what's the dependent variable. If those two things form together in an equation like a directly proportional relationship where you've got y is equal to the gradient m times x, then you know it's directly proportional. When you get an equation that is going to be, and that was the dependent variable, that's the independent variable, when you've got the equations that are y is equal to x is equal to a constant, then that's inversely proportional. Guys, this is so important, and it's so important that you get this right. So please pay attention, practice lots, and make sure that you've got this very well clearly sorted out. In that way, we can relate the graphs of different relationships to their equations. Right, now let's take a few moments, take a deep breath, have a break, and we'll see you straight after that.